Hi, we're Ene, Eric, and Eduardo, the 3E team. In this video, we'll show you the progress of our project developed in Seminar 3. Before we begin, we want to share a context that highlights the relevance of the opportunity we are addressing. Mexico is facing a serious water crisis, aggravated by factors such as climate change, overexploitation of aquifers, and insufficient infrastructure for water management. In 2024, 75% of the national territory will be affected by some level of drought, significantly impacting both urban and rural areas. In Mexican households with an average population of 4, it is estimated that around 150 liters of water are wasted per day due to poor habits, from washing dishes and clothes to letting the water run while waiting for hot water to run during a shower. According to the EPA, approximately 20% of the water used in a shower is wasted while the user waits for it to reach the right temperature. Given that the average shower consumes about 65 liters of water, this 20% equates to about 13 liters per shower. In a household of 4 people, this waste could add up to almost 19,000 liters of water per year.
During Seminar 1, and based on the methodology described in the book on design and development by Ulrich and Eppinger, we established the mission statement for our product. Modernization of the shower system for homes. For installation in the exposed pipe of the existing shower system, reduces the time of hot water output when the tap is opened at the start of the shower, reduces water consumption, and has an efficient, adjustable, and comfortable flow. This description identifies the basic function of the product, avoiding implying a specific product concept and viewing it as a vision statement of what the product should be.
In Seminar 2, we carried out the target specification. Here, we worked to determine the metrics based on user needs, along with conducting the benchmarking. We also classified the metrics by level of importance in order to understand which ones we want to excel in, which ones we want to be among the leaders, which ones have an acceptable average performance, and which ones may not be as necessary and could be left unmet. At the end of the process, this gave us a clear vision of the metrics we must meet if we want to generate differentiation in the market. We also carried out the problem decomposition process, where we applied the clarify the problem methodology through functional decomposition by sequence of user actions, and decomposition by key customer needs. At the end of this process, we obtained 4 critical subproblems, which we worked on during Seminar 3.
This seminar addressed the stages of concept generation and selection. The following presentation demonstrates the concept generation process, which was conducted through internal and external searches and systematic exploration. Additionally, concept selection was addressed, where various concept screening and concept scoring techniques were applied to select those ideas with the greatest development potential.
These are the critical subproblems we've identified and will be addressing throughout this presentation. We met as a team to conduct an internal search, using our individual and group knowledge of the project to generate ideas. It's important to mention that we sought the greatest possible creativity in brainstorming, so we tried to be as thorough and creative as possible to tailor the information to each subproblem. Through the internal search, we relied on different methodologies to generate new ideas. These were very helpful in giving us a new approach to each subproblem. In this first critical subproblem, we use the methodologies direct analogy, what if, provocation, scamper, affinity map, and role play. As it was the first exercise carried out, we obtained a greater number of ideas. It is important to mention that the team's focus was to detect ideas that could help us in solving each subproblem. So in some cases, if we put how, it would look in our system. In other cases, they are only the idea. By using these methodologies, we were able to realize 43 new ideas for this critical subproblem. In the process of generating ideas for this critical subproblem, maintaining the desired water temperature constantly throughout the shower, the methodologies were used and 29 ideas were achieved to attack the subproblem in different ways. It is the same case in this critical subproblem. We try to use methodologies to create ideas, and at the same time, we focus on only generating the ideas. Later, these ideas will help us solve the problem and visualize how it would be integrated into the system. The application of these techniques has allowed us to explore a wide range of solutions to the critical subproblems of our shower system. We have learned that diversity of approaches, suspension of judgment, structuring of analysis, iteration, use of focus, and consideration of feasibility are key elements of a successful innovation process. Each technique offers a unique perspective and stimulates different types of thinking, in addition to suspending critical judgment. This allows for greater fluidity of thought and prevents premature criticism from inhibiting creativity. When searching for solutions, it was important to be open to exploring ideas outside the direct context of the problem. This encourages both conventional and disruptive brainstorming. It was crucial to create an environment where all ideas were welcome, even those that initially seemed far fetched. In the product development and process improvement process, gathering external information is a key step for identifying existing solutions, understanding market trends, and evaluating applicable technologies. This presentation explores the importance of external search and its benefits derived from investigating existing solutions and exploring new alternatives for our critical subfunctions or problems. The suggested strategies for collecting information from external sources are as follows: interview main users, consult experts, search patents, search published literature, evaluate related products, use the Oxford TreesFX database. To address this problem, solutions have been explored through biomimicry, patent analysis, a review of existing products, and innovative strategies in the industry. Nature offers efficient mechanisms for the movement and storage of liquids. In parallel, systems have been identified on the market, and patents allow us to evaluate an approach to generate an ideas to solve this subproblem. 20 new ideas were made for this subproblem, highlighting the benchmark related products, as they give us a perspective of what we can innovate in our project. 32 new ideas were made for this subproblem, highlighting the products related to the consultation with experts, giving us a new perspective on solutions that we had not thought of since they give us a perspective of what we can innovate in our project. By exploring patents and published literature, we identified previous innovations that could be adapted or combined with our design. Evaluating related products allowed us to analyze existing configurations, their advantages and limitations, which helped us establish optimization criteria. One of the most significant lessons learned from this process was the importance of leveraging existing solutions whenever possible, which allowed us to focus our efforts on unexplored solution areas that could represent an innovation for our project.
During the internal search stage, we used the selected tools: TRIZ, Bisociation, Biomimicry. This process was corrected as we had initially omitted some important steps within each tool. After making the corrections, we obtained concepts for the four subproblems using the three tools. The feedback from the doctors was very valuable for the proper correction and execution of the tools. Carrying out the correction allowed us to increase creativity, taking advantage of the knowledge we already have about the problem, the market, the established needs, metrics, etc. The objective was to foster ideas using our knowledge, experience, creativity, and internal resources. In this first stage, the TRIZ process was carried out, starting with the identification of the characteristic we wanted to improve. Then, we defined the characteristic that needed to be preserved without compromising what we aim to maintain. Using the technical contradiction based on the official TRIZ matrix, both aspects were cross-referenced to find the applicable inventive principles. From this process, a conceptual solution was developed that resolves the technical contradiction without sacrificing functionality or efficiency. This process was applied to all four critical subproblems. In this process, interesting ideas were obtained, such as a mechanism that transmits pressure through a mechanism activated by the person's weight, or also a system that automatically adapts to the inlet water conditions without manual intervention, etc. In the next stage, we used the bioassociation tool, in which we applied the process of connecting ideas from two different fields, that is, contexts that are not normally related, with the aim of generating a new concept. We aim to break traditional mental patterns, which would allow us to generate completely creative and innovative concepts. The first thing we did was select the problem. Then, we identified two unrelated areas by analyzing processes, structures, or principles, all with the goal of creating a new concept. Here we present some of the concepts that were generated. For example, a pressurized tank that is incorporated into the shower head. This tank can be air refillable or self-filling. And also the following concept: a hydraulic press that allows the pressure to be pre-calibrated and adjusted when necessary by the user, and manual pressure adjustable sprayer nebulizer. Finally, we used the biomimicry tool, which helped us generate more concepts by encouraging us to think about functions that nature could solve. To do this, the first thing we did was identify the function we needed. Then, we used the platform asknature.org to search for biological strategies. After that, we extracted the design principles, translated from natural solutions, into principles or strategies applicable to our design. We then used the extracted principles to create a design aimed at being innovative and functional. We would like to share some examples of the concepts that were obtained using this tool. In the concept classification tree stage, what we did was organize all the concepts from the four subproblems into a table. Then, repeated and similar concepts were grouped into a single subproblem. In the first subproblem, a total of 71 concepts were created, in the second, 60, in the third, 81, and in the fourth, 46. To make the work easier, we created codes based on the different methodologies, and we also reduced the concept descriptions to more specific ones. This helped us begin the classification process. For each subproblem, we divided the concepts into categories, creating branches that extended to two working groups. This process helped us reduce the complexity of the concept generation activities and also allowed us to identify some healthy competition among the concepts. Therefore, this stage of the method helped us to ensure a complete exploration of the solution space, prevent all ideas from clustering around the same line of thought, facilitate the comparison and combination of more diverse concepts.
After conducting internal and external explorations to generate concepts that would solve our four critical subproblems, we built classification trees. This tool allowed us to categorize the solutions and eliminate the least promising or repetitive ones, thereby reducing the number of proposals from 260 to 31 with the greatest potential. To facilitate visualization of these trees, we assigned each solution description an identifier composed of the critical subproblem number, the idea generation technique used, and a consecutive number as illustrated in the example. Critical subproblem 4, biomimicry technique, solution 4. Once the most promising solutions for each critical subproblem were classified, we used the concept combination table as a systematic method to integrate these solution fragments. The table organizes the critical subproblems into columns, displaying the concepts from their respective classification trees. To generate integrated concepts, we combine a concept from one subproblem with concepts from others. For example, concept 1 was formed by combining idea 1 from critical subproblem 1, idea 2 from critical subproblem 2, idea 4 from critical subproblem 3, and idea 2 from critical subproblem 4. Concept 1 is described as a system that allows water recirculation using a module that detects changes in pressure and temperature, As it passes through the mixing system with sensors, the cold water is diverted using autonomous pressure pumps. In this way, each of the 22 resulting concepts has a description that integrates the partial concepts of each critical subproblem. Below, we will show 12 of the 22 finalist concepts. Concept 4. A system that has a heating module that adds hot air to the water and mixes it using a static mixer, has a sensor module that measures the temperature and adjusts the flow by activating the automatic pressure pump module. Concept 5. A system that has a storage tank that receives cold water from the hot water pipe, has a thermostatic mixing valve that communicates with the tank sensors to determine that the water contained has reached the appropriate temperature. After reaching it, the pumping module is activated that adjusts the output pressure programmed by the user. Concept 7. An independent heating system that uses electrical energy to heat the pipe by magnetic induction, has a temperature and pressure feedback module by programmable sensors, corrects the water pressure by means of a pumping system that adjusts the pressure programmed by the user. Concept 8. A system that has a static mixer that is heated by a magnetic induction system. Initially, it heats the cold water coming from the hot water pipe. When it reaches the temperature, the thermostatic mixing module is activated, fed back by the temperature and pressure sensing module. It has a pumping module that allows the output pressure to be adjusted. Concept 10. An infrared air heating system which will use sensors to measure temperature and adjust it with a mixing valve, and simple sensors will adjust the pressure. Concept 12. A system that has a small water storage tank will be heated by magnetic induction and through a pressure pump and infrared sensors, the water will come out with pressure at a constant temperature. Concept 14. A system that has a stored water tank which recirculates the water and uses a thermostatic mixing valve with infrared sensors and automatic pressure pumps to maintain pressure. Concept 15. A system that heats water by magnetic induction, which is passed through a recirculation system to avoid overheating the water, and subsequently, with a cold air current generator, it is mixed with hot water by means of a thermostatic mixing valve and with infrared sensors and a pumping system. It ensures that the desired temperature and pressure. Concept 17. A system that allows hot air to pass through water, detects changes in water pressure and temperature, and adjusts using a static mixer, which allows for a homogeneous mixture of liquids and gases. Concept 18. A system that features magnetic induction heating and is used to preheat water from a small cold water storage tank, adjusting the mixture using valves controlled by temperature sensors and preventing low pressure with self-contained pumps. Concept 20. A system with a serpentine type pipe that is connected to the toilet with an additional tank that also functions as a pressure tank for water reuse, has a thermostatic water mixer to maintain a constant temperature. Concept 21. A system that heats the pipe and water by magnetic induction and has infrared sensors to measure the water temperature in real time, mixes with a static mixer which allows a homogeneous mix, and has an autonomous pressure pump in case the flow is not adequate. Multi-voting helped us narrow our list of concepts from 22 to 10. This technique allowed us to focus on those we considered most effective in comprehensively solving our critical subproblems. This technique allowed us to actively participate in the selection process with each team member, who received 7 votes to distribute among the 22 concepts. Continuing with the concept screening, the selection matrix was carried out. The following criteria were used to develop the matrix: reduces the time to reach the target temperature, reduces wasted water, heating capacity, allows for the capture, recycling, or reuse of clean water. Easy to install, easy to maintain. Easy to use, allows for output pressure regulation. We also use the Bosch electric heater as a reference concept to evaluate whether existing concepts are better, worse, or equal under the selected criteria. After this technique, we went from 10 to 6 concepts. To move on to the scoring matrix development stage, it was necessary to assign new criteria based on what is expected of the product from a more business-oriented perspective. These criteria are: it is easy to manufacture and assemble, allows modular design, adapts to existing installations, the system is durable, allows incorporating technological updates, the system is programmable. These criteria were weighted to reflect the importance of each in evaluating the concepts. Using the weights assigned to the criteria, the relative performance of each concept was rated from 1 to 5, where 1 is significantly worse than the reference, 3 is equal to the reference, and 5 is significantly better than the reference. For this point, different benchmarks were used from several of the developed concepts. The scores are shown in red in the table. Using this technique, the result showed concepts 7 and 17 as the most likely to be developed. To corroborate the result, the team decided to use the analytic hierarchy process, which allowed us to corroborate that the result coincides with the concept scoring matrix. Through this evaluation, 2 finalist concepts were selected. It's worth noting that concept 17 is considered the winner of this selection process, but we are considering other concepts that could complement each other and subsequently conduct another evaluation that could change the result. There is no doubt that this stage was arduous and complicated. From the constant generation of concepts to the screening and scoring to arrive at the 2 finalist concepts, this seminar was an exciting journey where we observed how the process converges to obtain results with greater possibilities of development. The team recognizes the potential for combining and improving current concepts. Therefore, we hope to have more refined models before the next seminar, which will serve as a basis for initiating Seminar 4. We have high expectations for the next seminar, with the goal of converging on a single concept. This concept will allow us to apply and develop the knowledge acquired in systems architecture and other subjects, thus refining the selected design. We greatly appreciate the learning and guidance provided by the instructors. Thank you.